Hello all, this is the webinar series, SSCA webinar series. It is my pleasure to invite Professor Anirban Chakraborti for his current paper that is being accepted for publication in Statistics and Applications in volume 24, issue 1 for this June publication, June 2025. So he's going to present his paper, Understanding North Atlantic Climate Instabilities and Complex Interactions Using Data Science. Professor Anirban, it's yours.
Thank you, Dr. Sourish, thus for inviting us to present our paper. So this paper titled Understanding North Atlantic Climate Instabilities and Complex Interactions Using Data Science was written with our PhD scholar, Ms. Alka Yadav, Dr. Sourish Das from Chennai Mathematical Institute, and Dr. Sudeep Shukla from AI for Water Limited in United Kingdom. So in the abstract, we talk about, the importance of climate change and how these climate variables and environmental variables like North Atlantic oscillation or sea surface temperature or sea ice extent interplay with each other. So in this study, we adopt a data-driven approach to explore the complex interplay between North Atlantic oscillation, sea surface temperature, and sea ice extent, revealing a critical instability rooted in positive feedback loops among these climate variables. Our statistical machine learning methodology examines the impacts of melting Arctic sea ice extent and the rising sea surface temperature on the North Atlantic oscillation, thereby understanding the weather patterns across the North Atlantic region. So as you see in the keywords, we have focused on what are called complex systems and these different types of variables and trying to understand what type of climate change we have. So the first question that might come to your mind is what is complex system? So typically the complex systems are made up of smaller parts or constituents which interact with each other, and we see the collective behavior of the system and how the system interacts with its environment. So systems that are complex have different and distinct properties that arise from these relationships. And typically what you see are nonlinear behavior, emergent behavior, spontaneous ordering, adaptation, and feedback loops. So here these snippets give you some examples of complex systems. In the first one, you have the collective motion of about 70,000 birds, some patterns which we see in the sky quite often. The second one shows about, the traffic system where people are trying to drive their car, and it's a social phenomena where drivers are interacting with each other. The third one is the movement of stock market prices, which result as a thing of trades between buyers and sellers. And the fourth one is like the Arctic sea ice system that we are considering here in this paper. If you want to know more details, then you can look at this special edition in the journal Science, which was published in April 99 and deals entirely with complex systems. So typically in complex systems, you use different types of tools. And in this paper, we have used, for example, nonlinear dynamics, pattern formation, and evolution and adaptation. So you will see that the types of tools and techniques that we've done are very interdisciplinary in nature and have stemmed from physics, from statistics, from computer science, from mathematics, and other subjects. So what we first see is like that Arctic sea ice has been melting and freezing depending on whether it's summer or winter. So during the summer, there is melting. Then during the winter, it freezes and it goes in a cycle. But what is interesting is that over several decades, we see that there is a shrinkage of the Arctic sea ice extent, and which is a concern for people who are trying to protect the planet, because if the Arctic sea ice thing shrinks, there's more water in the sea level rises, and it can cause havoc in the entire planet. So it is important for us to understand the behavior of this Arctic sea ice extent melting, and how it affects the other weather variables. So the most important thing that we see is the effect of the sea ice extent and the North Atlantic Oscillation. Now, the North Atlantic Oscillation is the difference of atmospheric pressure at sea level between the Icelandic low, which is around here, and the Azores high, which is around this part. And you typically have two types of phases. One is called the positive now phase, and the other one is called the negative now phase. And when there is a positive now phase, you typically see that there is a warmer part in the northeastern part of USA and a warmer and wetter weather in the northern Europe and colder drought region in the southern Europe. Similarly, in the negative thing, you have the colder storm and dry in the northern part, cold and snowy in the eastern part of the US, and you have warmer and wetter winters in the southern part of Europe. So the type of data that we have used are all available in the public domain. We have a data set from the National Oceanic and Atmospheric Administration website, which is called the NOAA, and it gives you different types of variables, including the sea ice extent, which is like you see the pattern in blue, the North Atlantic Oscillation, which we have plotted in this green, and the sea surface temperature, which is in this red. So you see that there are seasonal patterns, but also there are trends, long-term trends. And so what is interesting is to note how these different climate change variables interplay with each other. So in order to model the sea ice extent analysis, for example, what we have done, if xt is the sea ice extent at any time t, then we have a trend part, which is represented by these first three terms. And then we have the seasonality part, which we have this different sines and cos terms, which is basically a functional analysis of the variables. So in the seasonality component, we consider the periodicity, which is the daily one. So 2 pi divided by 365. And then you can also take the change in the sea ice extent, so x prime t and also double x prime t. And so we try to look at these equations and then we try to model using functional data analysis. The other type of tool that we have used is, for example, the Granger causal models. So, for example, we have made the null hypothesis that the now index is function of only its historical memory. So then you model it with this equation. The alternate hypothesis is no, the now index is not only a function of its historical memory, but it also is the function of historical momentum of sea ice extent. And then you have this alternate hypothesis. And then when we test, we find that actually the null hypothesis is rejected, which means that now actually has an effect. We've also used a technique called the Kalman filter updates, because one criticism of previous studies was that, for example, these coefficients that you have are fixed over time. But then we realized that no, these terms, beta 0, beta 1, and other terms can also be functions of time. And so we use what we called a Kalman filter update equations. The derivations are given in the paper, and we see how the intercept changes or how the sine and cosine coefficients change, which show that the beta 0, beta 1, beta 2, and the other parameters, which are typically taken as constant, actually do vary over time. And so this technique addresses the criticism that they don't change over time. So what is the novelty and significance of this paper? The studies of the cross-correlation functions, which are given in the paper, indicate that there are lead and log cross-correlations between the now, the SIE, and the SST. The Granger causal test shows that now is affected by SIE and SST. what is new about this paper is that we did all this analysis on a much larger scale. So our approach is very statistical and different from the climate models. And we addressed a lot of criticisms present in the previous studies, and we have used very interdisciplinary techniques. So the summary is like I showed you that there is a grandeur causal between these different variables. The anti-correlation implies that the increasing SST trend is likely to trigger increased occurrences of negative now, and that means the weather pattern will change. And this underscores the significance of this study in predicting a notable climate change. So that is typically the type of study we have done here. Thank you. And if there are any questions, I can.
Thank you, Professor Chakraborti. You finished right exactly at the 10 minutes your scheduled time. Thank you for being on time. Anybody have
Thank you.
any question? Okay, thank you once again, Professor Chakraborti.
Thank you.
We will put the video on YouTube very soon, and it will be available to the world very soon. And also the link will be available in the paper in the forthcoming issue. Thank you very much.